Hello students, this chapter of movement of inertia plane areas is for autonomous colleges of Mumbai University like for BJTI, for SPC and even for Mukesh Patel and other autonomous institutions, right? At previous level, you have learned moment of inertia of the masses where the unit of mass moment of inertia was kg meter square or kg centimeter square. In this lecture, in this part, we will learn the moment of inertia of plane areas. Now, let's first understand the definition of moment of inertia. Now, here I have shown a lamina of area A. OX and OY are the two reference axes in the plane of the lamina. Assume that dA is area of elemental part. We are assuming one elemental part having elemental component having area dA. Assume that x is the perpendicular distance of this elemental part from x's reference axis OY. Then summation dA x1 is, we consider that this area is split into infinite number of elemental components having area dA. One such component is shown at distance x. So assume that one component is at distance x1, another is at x2, another is at x3. Then summation dx1 square plus dx2 square plus dx3 square or summation dx square or integration of dx square is called as moment of inertia of the lamina about reference axis OY. Similarly, suppose this area is split into infinite number of elemental components of area dH. Then suppose y1, y2, y3, y4 are the perpendicular distances of these elemental components of reference axis OX. Then dA at y1 square plus dA y2 square plus dA y3 square or summation dA y square or integration of dA y square is called as second moment of area or moment of inertia of the lamina. Second moment of area of the lamina. This is slight correction is that this is second moment of area of the lamina, not inertia. Second moment of area of the lamina or moment of inertia about axis OY. All right, because moment of inertia is second moment of elemental area. Second moment of whole area cannot be done. So moment of inertia is defined as second moment of elemental area. That means elemental area should be multiplied by the perpendicular distance twice. So that becomes the second moment of elemental area. And you get the initially moment of inertia of the elemental area about the axis. Then if you integrate with appropriate limits, then you get the moment of inertia of the whole area about that reference axis. But you cannot, you can integrate with the appropriate limits, then you get the moment of inertia about the reference axis. All right. What are the commonly used units for moment of inertia? Mm raised to 4, centimeter raised to 4, or meter raised to 4. Now, this is the difference what it comes. You'll see that now parallel axis theorem, perpendicular axis theorem, what you have learned in the chapter of mass moment of inertia at previous level. Identically here also you will have parallel axis theorem and perpendicular axis theorem on identical lines. Now we'll learn perpendicular axis theorem. Now you have the lamina of area A. OX and OY are the two mutually perpendicular axes in the plane of the lamina. OZ is the axis which is perpendicular to the plane of lamina and passing through the point of intersection of the two reference axes OX and OY. If moment of inertia of this lamina about axis OX is IOX, moment of inertia of this lamina about axis OY is IOI, then moment of inertia of this lamina about an axis OZ, which is perpendicular to the plane of lamina and passing through the point of intersection of these two axes OZ, IOZ is equal to IOX plus IOI. Hope you understand it. Identically, we had learnt it for mass moment of inertia. I repeat again, IOX and IOY are the moment of inertia of this lamina of area A about OX and OY. OX and OY are the two mutually perpendicular axes in the plane of the lamina. IOZ is the axis which is perpendicular to the plane of lamina and passing through the point of intersection of the lamina. IOZ is equal to IOX plus IOI. This is what is the statement of parallel axis theorem. Then we will derive also. Now here you should understand OZ axis also called as polar axis. Moment of inertia about polar axis also called as polar moment of inertia. Now to derive the perpendicular axis theorem, I'm considering the same lamina of area A. I'm considering one, assume that it is split into infinite number of elemental components of area DH. One such element has been shown on the diagram, right? DA. Same IOX and IOY is the moment of inertia of this plane area about OX and OY axis, which are in the plane of lamina. OZ is the axis perpendicular to the plane of lamina and passing through the point of intersection of these two axes. All right. Now we consider that R is the perpendicular distance from axis OZ. OZ is like this. All right. So moment of inertia of this elemental area dA about axis OZ will be dA into R square. What will be that? Moment of inertia of the elemental component about axis OZ is dA into R square. But we know that if you complete a right angle triangle here, we understand that x square plus y square is equal to R square. All right. So substitute the value of R square. So moment of inertia of the elemental component about axis OZ is dA x square plus y square. We substitute the value of R square. Then we open the bracket and we find the moment of inertia of the whole lamina about axis OZ. So what will you use it? Either you use here integration sign or use summation. Summation sign is used for theoretical explanation, but if there is a numerical or there is a definite values are given or definite dimensions are given, then you have to use the sign integration. So here we write it summation dA x square plus summation dA y square. Summation dA x square is nothing but I O y and summation dA y square is nothing but I O x. So this way we derive the perpendicular axis theorem. Derivation is also quite identical to what we learned at previous level for mass moment of inertia. Let's move to the parallel axis theorem. Okay, students. Now first we'll understand this statement. Look at this diagram. This is the lamina of area A. All right. X-axis is centroidal axis, horizontal centroidal axis. AB is any axis parallel to centroidal axis. Perpendicular distance or distance between the two axes AB and XX is y. So parallel axis theorem states that moment of inertia of the lamina of area A about any axis parallel to centroidal axis is equal to sum of the moment of inertia about centroidal axis and product of area and the square of the distance between the two axes. So IAB is equal to IXX plus AY. Now we'll go for the derivation of it. On the right side, you can see that same I have taken the area of lamina of area A. I have assumed one elemental strip, elemental area dA, right? This is centroidal axis XX. This is reference axis AB. Distance between two axes y bar. Y is the distance between centroidal axis and elemental area. Then moment of inertia of this elemental area as per basic definition about axis AB. Will it be second moment of area or not? So dA into y plus y bar square. So moment of inertia of the elemental area dA about axis AB is what? dA into y plus y bar square. All right. Then moment of inertia of the whole lamina about AB is, you need to, again there is no definite dimensions are given, so you carry out summation dA y bar plus y. Open out the bracket. This is summation dA y bar square plus summation dA y square plus 2 times of summation dA y bar I. Now we understand that summation dA is area A to just wait for a minute. Yeah. Okay. So moment of inertia, there was some internet problem. We connect again. So we were discussing that moment of inertia, the whole lamina about axis AB is what? Summation dA y bar plus y whole square. So open out the bracket. Summation dA y bar square plus summation dA y square plus 2 times of summation dA y bar. We know that summation dA is total area. Summation dA y square is Ixx as moment of inertia of the lamina about centroidal axis. Since Xx is centroidal axis, first moment of area is 0. right? This summation dy is 0 since x-axis is centered axis. So finally, we prove that IAB is equal to Ixx. This is Ixx, and this is plus a y bar square, and this term is 0. So this way, students, we prove that IAB is equal to Ixx plus a y bar square. As in this diagram, again I repeat, moment of inertia of the lamina about any axis parallel to centroidal axis is equal to sum of the moment of inertia about parallel centroidal axis and product of area of lamina and square of the distance between the two axes. So IAB is equal to Ixx plus a y bar square. Now, students, we come across various elements or various elements in this when we are going to solve the problems of composite area. One of the elements is rectangle. So various elements are what, like rectangle, square, circle, semicircle, quarter circle, etc. Right here, if you refer to my book, you'll find the derivation of all the components. But here in the lecture right now, I'm just taking the derivation of only one component. So I'm going to discuss rest all. I'll give you the formula and how to remember it for solving the problems. Now, let's come to a rectangular lamina is given to you of dimension b is base width and height h. X-axis is horizontal centroidal axis, y is vertical centroidal axis. We want to derive the moment of inertia of this rectangular lamina about x-axis. So I took one elemental strip of area dA, right? This strip is of width b and thickness dy. So elemental area dA will be b into dy. We want to find moment of inertia of this elemental strip about x-axis. So I'll write it dIxx. What to write it? Moment of inertia of the elemental strip about x-axis will be elemental area into square of the distance between the two. So summation dA y square. Y dA is b into dy. We understood it, elemental strip area. So now you want to find moment of inertia of the whole area about central axis. So this expression should be integrated with appropriate limits. You are going to integrate here with respect to y. So you are measuring y from x-axis. So lower limit will be minus h by 2, upper limit will be plus h by 2. That is clear. Now it is lower limit is minus h by 2, upper limit is plus h by 2. So we can write it this as 2 times of 0 to h by 2. So b also I have taken outside constant 2 times of y square dy. Y square integration is what? Y cube by 3. Lower limit 0, upper limit h by 2. Then 2b by 3, h by 2 cube minus 0 cube. So you get it 2 by b by 3 into h cube by 8. So finally you get it Ixx is equal to bh cube by 12. Moment of inertia of the rectangle about xx centroidal axis arrived at bh cube by 12. Similarly, we can prove that moment of inertia of this rectangle about centroidal axis yy is hb cube by 12. And moment of inertia of this lamina about AB can be obtained once Ixx has been derived. You can find IAB by using parallel axis theorem. So what will be moment of inertia about AB? Ixx plus AY bar. So Ixx is bh cube by 12. Area is b into h. Distance between xx and AB is h by 2 whole square. Bh cube by 12 plus bh cube by 4. So this comes out to be bh cube by 3. So this way we find moment of inertia of the rectangle about base AB is bh cube by 3. Similarly, even ICB will also be bh cube by 3. If you find moment of inertia of this rectangle about AD or about BC, this will be HB cube by 3. We'll understand it in the next slide, how to remember the formula for solving the problems. Even if you want to find moment of inertia of this rectangle about polar axis through G, xx and yy are two mutually perpendicular axes. Polar axis through G will be perpendicular to the plane of the lamina. It will be equal to Ixx plus Iyy. Ixx is bh cube by 12, Iyy is hb cube by 12. Students, in my book, I have done the derivation for triangular lamina, circular lamina, right? Then semicircular and then quarter circular. Right now, one component rectangle I took it and I just gave you the idea how the derivation for standard formula is done for the various components. All right. Right now, we are moving to the formula sheet, what way the formulas are to be remembered for solving the problems. One more theory part, I'm just taking it before we move to the problems, is radius of gyration. This term is right now not that important, but when we go to the next level and learn the subject next year, that is strength of materials, mechanics of solids and all, the importance of this term will be more. as you had learned radius of gyration term even at previous level also. What was the formula where radius of gyration, how it was defined? Over there, when you are dealing with mass moment of inertia, right, radius of gyration was moment of inertia upon mass. Here, same thing, it will be expressed in terms of area. Now, this is the lamina of area A. Ixx and Iy are the moment of inertia of this lamina about reference axis, xx and Iy. Now you want to find radius of gyration with reference to x-axis. So this area is assumed to be concentrated into a thin strip. At what distance this strip should be placed so as to give the same moment of inertia? That distance is called as k-axis. See, ix is moment of inertia of this whole area about x-axis. So suppose this area is concentrated in thin strip, then you can find the moment of inertia of this thin strip by taking second moment of area. What will be second moment of area? A into kxx square. So ixx is equal to A into kxx square. So kxx is square root of ixx upon area. So kxx will be radius of gyration of the area with respect to x-axis. Similarly, Yy. This is I, not Ixx, this is Iyy. Similarly, Iyy is A into Kyy square. Kyy is Iyy upon. So in this case, it is assumed that entire area A is assumed to be concentrated into thin strip at a distance Kyy. So Kyy is radius of gyration of the area with respect to y-axis. So it is just right now at mechanics level, you can just remember the formula that Ixx is equal to A kxx square and Iyy is equal to A Kyy square. All right, that's it. But at higher level, while solving, while moving to the next level of learning, then importance of this radius of gyration is. Now we are coming to students to the formula sheet, standard formula, what we should remember. We have already discussed with you perpendicular axis curve. This is just a formula sheet, right? No derivation, nothing in this formula sheet. Now this is the lamina of area A. OX and OY are the two mutually perpendicular axes in the plane of this area. So moment of inertia of this lamina about OX axis IOX, about this is IO. So OZ is the axis perpendicular to the plane of area and passing through the point of intersection of the two axes. So IOZ is equal to IOX plus I. Parallel axis theorem, as already discussed, IAB is equal to IXX plus AY bar square. Sorry. Moment of inertia of this lamina about any axis parallel to centroidal axis AB is equal to sum of the moment of inertia about parallel centroidal axis, that is IXX, and square and product of the area and square of the distance between the two axes. So IAB is equal to IXX plus AY. Now we'll come to the components. Rectangular component I had completely derived. How will you remember it? You have a rectangle of base width B and height h. Xx is its centroidal axis parallel to base. So moment of inertia about any centroidal axis will be bh cube by 12. Now you have to understand meaning of B. B means what? Parallel dimension. Parallel is B. And other dimension is cube. Like that we need to remember. Moment of inertia of the rectangle about centroidal axis is what? Bh cube by 12, where B is parallel dimension, h is other dimension. Now moment of inertia of the rectangle about base is bh cube by 3. B is base width and h is other dimension. BH cube. Similarly, square moment of inertia of the square of size B is about any centroidal axis. Moment of inertia is B raised to 4 by 12. And moment of inertia of the square about each base is B raised to 4 by 3. It is absolutely, it is extension of rectangle. Now we come to triangle. Moment of inertia of the triangle of base width B and height h about centroidal axis parallel to base is BH cube by 36. And moment of inertia of this triangle about base is BH cube by 12. Come to circle of radius r. Moment of inertia of the circle about each centroidal axis in the plane of lamina, whether it is xx or it is yy or any other centroidal axis in the plane of circular lamina passing through the centroid is pi r4 by 4. Then we come to semicircle. In case of the semicircle, right, this is called as base. This is centroidal axis, which is called as axisymmetry. This centroidal axis is parallel to base at a distance of 4r on 3. Right? We know it already from the centroid chapter. So we should remember it like this. Moment of inertia of the semicircle about base and about axisymmetry is pi r4 by 8. Exactly half of what it's for circle. For circle, it was pi r4 by 8. So moment of inertia of the semicircle about axisymmetry and base is pi r4 by 8, half of that. And moment of inertia of the semicircle about centroidal axis parallel to base is 0.1098 r raised to 4. This has been derived in my book, All right, under the derivation category. All right. So we'll remember it. Moment of inertia of the semicircle about base and about axis-symmetry is pi r4 by 8. And moment of inertia of the semicircle about centroidal axis parallel to base is 0.1098 r. Then we come to quarter circle. In case of the quarter circle, moment of inertia of the quarter circle about base OA and OB is same. What is that is pi r4 by 16, 1/4 of what is for the circle. So moment of inertia of the quarter circle about each base is 1/4 the circle pi r4 by 16. Then moment of inertia of the quarter circle about centroidal axis parallel to base is what it is, half of what we got it for semicircle, half of 0.1098 r raised to 4. So 0.1098 r raised to 4. Now next, students, it's a working methodology. Important points for solving moment of inertia problems. Now, you are given with the composite area and they're asking you to find the moment of inertia of the composite area about reference axis. When I use the word reference axis, that means any axis other than centroidal axis is called as reference axis. So moment of inertia of the composite area about reference axis is obtained directly. Next, we come to centroidal axis. Centroidal axis will be of two types. One is axisymmetry, another is centroidal axis, other than axisymmetry. Suppose this is axisymmetry. This is centroidal axis other than axisymmetry. So whenever for composite area, you are finding moment of inertia about centroidal axis other than axis of symmetry. So we go for indirect approach. What is indirect approach? We first find the moment of inertia of the composite area about parallel reference axis. Then we apply parallel axis theorem on the composite area so as to find the moment of inertia about parallel centroidal axis. Third type of the problem where moment of inertia of the composite area is required about axisymmetry. So that we go directly. Only moment of inertia of the when moment of inertia of the composite area is required about centroidal axis other than axisymmetry, we have to take indirect method. So moment of inertia of the composite area is required about centroidal axis, that is axisymmetry. Then moment of inertia of the composite area about axisymmetry is obtained directly. Another precautionary note. Base formula for any component is to be used only when the base is touching the axis about which moment of inertia is required. Otherwise, we should not use a base formula at all. For finding moment of inertia of the composite area about horizontal centroidal axis, we need y bar. Similarly, for finding moment of inertia of the composite area about vertical centroidal axis, we need distance x bar. All right. So I think we are ready to start with the problems. First problem. Find the moment of inertia about horizontal and vertical centered axis for the angle section shown in figure. Students, if he is asking moment of inertia about the centroidal axis, you need to mark the centroidal axis on the diagram. Either you understand it by symmetry or you do it by working. In whatever way you do it, you need to mark the centroidal axis for which the moment of inertia is required. Now this L-shaped section, first you have to split it into the standard components. So I'm just putting this line as dotted line here. So I'll take one component is this rectangle of 10 mm width and 125 mm. Another component, I'll take it 65 mm width and 10 mm. So we have drawn the diagram. There is no axisymmetry of this composite area. So we'll find x bar and y bar. Suppose I find x bar, so we find it from the reference axis O. What is that x bar? A1 x1 plus A2 x2 divided by A1 plus A. Now A1 is component number 1. What is the area? 10 into 125. X1 is this distance 5. Come to the second component, area is 65 into 10. X component of the centroid of it from y-axis is what? 10 plus 32.5. 65 by 2, 65 32.5 plus 10, that is 42.5. Divided by A1 plus A2. A1 is 125 into 10 plus A2 is 65. You get it x bar as 17.5. Similarly, we get y bar. Y bar is this distance between OX axis and XX axis, right? What is y bar? A1 y1 plus A2 y2 divided by A1 plus A2. A1 area is 10 into 125. Centroidal y coordinate of centroid of this from the axis OY is what? 125 divided by 62.5 plus this area 65 into 10. Y coordinate of centroid of this component is 5 divided by A1 plus A2, you get it. Total area of this angle section is A1 plus A2, that is 1900. I mean, this is denominator of this expression of this expression. Students, here we have found x bar and y bar. X bar is the distance between y reference axis and y by centroidal axis, marked in x bar 17. Y bar is the distance between x reference axis and x centroidal axis, that is 42.8. Both the centroidal axes are other than axisymmetry, so we'll have to take indirect method. What is indirect method? I'll not find moment of inertia about xx directly. First, I'll find about ox and then apply parallel axis theorem on the whole. It is not that you cannot find moment of inertia about xx directly, but as a learner, as a beginner, we should use indirect method. So first, getting moment of inertia of this composite area about ox is easier, and then getting it about xx is using parallel axis theorem. So first, we find moment of inertia about ox. See that. This first component of base width 10 and depth 125, is it touching the OX axis or not? Base of this component 1 is touching the reference axis OX, so we can directly apply base formula. So what is that? Base of rectangle, moment of inertia of the rectangle about base, BH cube by 3. So B is 10 parallel dimension into 125 cube by plus. Second component, this rectangle of width 65 and depth 10 is also touching. Its base is also touching x-axis, so directly base formula can be applied. Base formula is what? BH cube by 3. B is this time 65 into 10 cube by 3. You get it IOX. But we know that for this composite area, IOX is IXX plus A by bar square. IOX is this value. IXX is needed. Area is 1900, we got it. And Y bar is 42.8. Substitute all this, you get it IXX. IX is 3.047 to 10 raised to 6 mm raised to 4. Unit will be, as all dimensions are in mm, moment of inertia, the unit will be mm raised to 4. Identically, we'll find moment of inertia about O. For first component is resting, base of the first component is touching the reference axis OY, so base formula can be directly applied. What is moment of inertia of this component 1 about OY is what? 125 into 10 cube by 3 plus second component. Second component moment of inertia about OY cannot be obtained directly. First, we have to find moment of inertia of this about parallel centroidal axis. So what is that? 10 into 65 cube by 12 plus 10 into 65. Distance between the two axes is 10 plus 32.5, that is 42.5 square. You get it IOY 1.444 into 10 raised to 6 mm raised to 4. But we know that using parallel axis theorem on the composite area, IOY is equal to IYY plus A x bar square, right? IOY is known to you, area is known to you, x bar is known to you. What is x bar? We have already marked it on the diagram, 17.83. So substitute the value of IOY, area, and x bar. You get IYY, that is 840.56 into 10 raised to 3 mm raised to 4. All right. So this way we found the moment of inertia of this angle section, or we call it as L-shaped section, about the two central axes. Once again, I repeat that if examiner is asking you to find the moment of inertia about central axis, you need to mark the central axis on the diagram at all, either by axisymmetry knowledge or by centroidal plan. Okay. Now we take another problem. Find moment of inertia of the given channel. C-shaped section is called as channel along the two central axes. Again, he is asking moment of inertia of this C-shaped section or channel section about two central axes. So what will be my first job? Draw the diagram, mark the two central axes. Now I took this OX and this is OY. All right. This component is 16 to 20. This component is 16 to 20. Middle component is base width is 20 and 120 minus 20 minus 20, that is 120 minus 20 minus 20 is 80. So this is your 80 mm, 20 mm, 80 mm. So all the three components are well defined. Component number 1 is of base width 80 and height 20. Component number 2 is of base width 20 and height 80. Component number 3 is of base width 60 and height 20. All right. Now we can understand that due to symmetry, y bar, the distance between OX and XX axis is, due to symmetry, it is equal to 120 by 2. We understand that XX centroidal axis of this component, horizontal centroidal axis, nothing but axis of symmetry. How come it is axisymmetry? Axisymmetry is the line that divides the composite area into two equal parts so that one part is mirror image of another. So since x-axis is axisymmetry, y bar is 120 by. So distance between x-axis and o-axis directly obtained as 16. But x bar, central axis y is not axisymmetry, so we have to locate it through y. So x bar is equal to a1 x1 plus a2 x2 plus a3 x3. First area is 60 into 20. Centroidal distance from reference axis y is what? 60 by 2, 30. Second component is 20 into 80 and x1 is 10. Third component is 16 into 20. X coordinate of centroid of it from y reference axis is what? 30. Divided by a1 plus a2 plus a. You get it 22. Area of this channel section or whole area is summation A. This is denominator of this. This is 4,000. Now students, here Ixx is, this is xx centroidal axis axisymmetry. So its moment of inertia can be obtained directly, should be obtained directly as per our methodology. So how are we finding? Ixx is equal to solid. Solid area is what? 60 into 120. 60 into 120, bh cube by 12. 60 into 120 cube by 12. Minus for the hollow part, this is 40 into 80 cube by 12. All right, either. Calculated directly at solid minus hollow. Now the question comes that this solid minus hollow for centroidal axis can be done when? When for the composite area, centroidal axis, actual centroidal axis and centroidal axis the solid part and centroidal axis the hollow part are coincident. Then only this way directly you can do it solid minus hollow, otherwise no. Then moment of inertia about y axis. Since y centroidal axis is not axisymmetry, so you have to do it indirectly. How do you indirectly? First we'll find moment of inertia about axis over. So what will be I over? See, component number 1, its base is touching the reference axis over, so base formula can be applied directly. What is that? 20 into 60 cube by 3. Second component, base is again touching the reference axis OY. Again, direct formula can be applied. BH cube by 3. B is 80 into 20 cube by 3. Second component, third component is this. Its base is again touching reference axis OY. Again, you can apply direct base formula BH cube by 3. B is 20 into 60 cube by 3. So if you add them up, you get it IOY. But IOY is equal to IY plus AX bar square, right? IOY is known to you. Area is known to you 4,000. X bar is 22. So you get I 1.1573 to 10 raised to 6 times. All right. This way, we understand that moment of inertia of the composite area about axis of symmetry is obtained directly. As Ixx, we got it directly. And Iyy, we got it indirectly by finding first moment of inertia of the composite area about parallel reference axis and then applying parallel axis on the whole area to get the Iy. Just a minute, just a minute. We're back. Now we are taking the third problem. Find the moment of inertia of the given symmetrical I section about x centroidal axis and y centroidal axis. Now, if you will first observe the difference between this problem and the previous problem. In the given I section, both the centroidal axis, horizontal as well as vertical centroidal axis, are axes of symmetry. So we can mark the centroidal axis without doing any centroidal working. As you can see that this is horizontal centroidal axis, this is also axis symmetry. Vertical centroidal axis is also axis of symmetry. All right. So we have marked it directly. Right. Now we can find the moment of inertia about xx and yy directly. How will you find moment of inertia about xx directly? We will do solid minus hollow. When you can do solid minus hollow, I have written a note here. Can you see that? Ixx can be calculated on solid minus hollow part. This approach can be applied only when centroidal axis of the given section, I section, and solid section, rectangle, minus the hollow part, all are coincide, right? So we'll take it moment of inertia with x-axis as solid minus hollow. What is moment of inertia of the solid part? Solid is 100 into 200 cube by 12 about x-axis. If it is entire area is solid, then moment of inertia of this solid rectangular part about x-axis is at 100 into 200 cube by 12 minus for the hollow part. Hollow part total width is 200, total width is 100, minus 10 is 90. This hollow and this hollow part put together width is 90, minus 90 into depth is 180 cube by 12. So this way I-axis is obtained. How will you get IYY? Moment of inertia of this I section about YY will be obtained directly. How do you get it directly? Right? You take moment of inertia of this component 10 into 100 cube by 12. This one 10 into 100 cube by 12. So we have made it twice. Middle component directly again you can get it because central axis is coinciding with the axis of YY. So 180 into 10 cube by 12. Again I repeat it. This component is coinciding with YY, so moment of inertia is found directly 180 into 10 cube by 12. This component about YY 10 into 100 cube by 12. This component 10 into 100 cube by 12, so we made it twice. So this way we got moment of inertia. So this way, students, in this lecture we have covered 3 problems of moment of inertia of the composite area. First problem was of angle section, second was channel section, third is I section. This type of sections are very commonly used for a structural engineering purpose as beams. All right, their application of these sections will come at next level of learning in strength of material. All right, this part or this chapter, let me tell you, is not there for MU Mumbai University student. It is there for autonomous colleges like BJTI, SPC, or Mukesh Patel, or other colleges like Ramarao Adik or some other colleges which are autonomous. Right? Maybe it is there for even Somaya also. Right? You can check your syllabus and accordingly you can watch this video. Now, students, as I told you in the beginning, I have covered major part of the derivation of this chapter in my lecture right now, except few derivations I have not covered because you get bored while watching the video lectures of derivation. So all the derivations are given in my book. Book is available on Amazon. All right, its link is given in the description of this video lecture. All right, for every chapter, I have given lot many MCQs. All right, which are also there in the book. These video lectures are completely free for all. Nothing to do with buying the book also, because these are based on everything is there in the lecture. So I have explained it in such a way that even if somebody wants to watch only video lectures, can also gain full understanding of the topic. So please share the QR code of my YouTube channel with your friends so that they are also benefited with my free video lectures. All right. Its second part will cover some more problems on moment of inertia. It will be uploaded soon. Thank you.